All right, welcome back from spring break. This is video 1 for week 11. And we're going to slowly introduce ourselves back to all of our different shapes. So the first shape we're going to talk about is a triangle. We all know this. We've talked about it. We just got done with our trig, which is all about right triangles. Let's just go back and remind ourselves and learn something new about triangles that we're going to use for this unit. So what we're going to use is called a Freyer model, and we're going to use this for all of our new definitions. So a Freyer model looks like this. It's just a rectangle broken into 4 parts with our vocab word in the center. So our triangle is a polygon with 3 sides. A polygon, right, is a straight-sided connected shape. Examples, right? We have right triangles, we have acute triangles, we have obtuse triangles, we have scalene triangles, and we have isosceles triangles, right? Non-examples, if we have 3 sides that aren't connected, if we have a 4-sided shape, if we have a circle, all these things are non-examples. And the facts that we have that we are going to use a lot this unit, and we might actually come back and add to. Number 1, we know that the 3 angles add up to 180 degrees. If it's isosceles, right, which means the 2 sides are the same, then the 2 base angles are congruent, right? And remember, here's our base, here are the congruent base angles, here are our 2 congruent legs. And that's if we have an isosceles triangle. And then the last thing we're going to learn about triangles today is what we call a mid-segment. But we'll come back and talk about that once we just go over some examples of using those first 2 properties. So, the first 2 properties of our triangle. We said if we had a triangle, we know their 3 angles, add up to 180. We actually did that in classwork, right? We ripped off the 3 corners and then assembled them right next to each other, and we saw that it made a straight line. They add up to 180. So if we have this scenario, we have 50 degrees, we have 37, and we want to find x, we can do that by doing 37 plus 50 plus x equals 180. We add those 2 together to get 87 plus x is equal to 180. So that way we get x is equal to 93 degrees. We can get a little bit more complicated, right? If we have another triangle and we say this is like 2x plus 1, this is 4x plus 20, and maybe this is 52. I just made that up. We'll see if we get a good number for x, but let's see, right? We take those 3 things, we add them up to each other, and we set it equal to 180. So then we combine like terms, so we get 6x plus 73 equals 180. So 6x equals, right, we subtract to get 6x is equal to 107, and then we divide by 6, definitely aren't going to get a nice clean number. What we do get, though, 107 divided by 6 is equal to 17.83, which then we can plug back into our expressions to get our individual angles, right? So we do 4 times 17.83 plus 20 to get about 91.3 degrees. And then down here we do 2 times 17.83 plus 1. And that's 36.7 degrees. And we can check our work by adding that together. We get 36.7 plus 91.3 plus 52, and we do get 180. Right, so those are 3 angles in this triangle. Our second property said if our triangle is isosceles, right, and sometimes we see that because they have these tick marks, so that means it's isosceles. That means these 2 angles are the same. So with no x's, if we just say this was 40 degrees, we would do 180 minus 40 is equal to 140. And that's shared between the 2 congruent angles, so we divide that by 2 to get 70, right? If we had another isosceles triangle, sometimes they show it to us by doing this. This is 10, this is 10, and this is 19. So because these are the same number, that means these 2 angles on the base, the odd man out, are congruent. So let's look at a more complicated example. Maybe our angles here, this is 70, no, it's definitely obtuse. This is 115. Let's make that, 110. And then this one would be 3x plus 5. So here what we can do, because this is an isosceles triangle, because both these sides are 10, this one over here is also 3x plus 5. So we can do 110 plus 3x plus 5 plus 3x plus 5. Right, we have those 2 same angles equals 180. Combine like terms, we get 120 plus 6x is equal to 180 minus 120 on both sides. 6x equals 60. Divide by 6, so we get x is equal to 10. We're not done yet, we need to plug it back in. 3 times 10 plus 5 is 35 degrees. Again, because it's isosceles, this one's also 35 degrees. We can check our work. 35 plus 110 plus 35 is 180. So that was the first 2 rules, properties of a triangle. The new one says, if we have this triangle, let me not draw it as an isosceles triangle. If we have this random triangle and we find the midpoints on these 2 sides and connect it, number 1, this line right here is called the mid segment. And our property says, right, if we draw the mid segment, then it is half of the third side of the triangle, which is parallel to the mid segment. All right, so in this example, we know that's the mid segment because we drew it like that and we could have these tick marks. If we said this bottom side is 40, using our property, which we got, if we wanted to look at the proof, by our similar triangles, if this base is 40, this third side is 40, that means the mid segment is just half of that, so it's 20. But let's look at a little bit more of a complicated scenario. We have a triangle. I'm going to draw a mid-segment. All right, and I'm going to label some of these sides. I'm going to say that the mid-segment is 2x plus 4. And then over here, we're going to say that the whole segment, this third side, is going to be equal to 7x minus 1. We have to somehow figure out what x is and then plug it back in to figure out what each part of this triangle is. So to do this, we have to use our property. We said the mid-segment is equal to 1/2 of that side. So we say the mid-segment, which is 2x plus 4, is equal to 1/2 of 7x minus 1. I don't like that 1/2, so instead of trying to distribute it, I'm going to multiply both sides by 2. So I'm going to get 4x plus 8 equals 7x minus 1. I'm going to combine like terms. And then I'm going to divide both sides by 3 to get x is equal to 3. I'm not done. I need to plug it back in, right? 7 times 3 minus 1. 21 minus 1 is 20, so the whole side is 20. 2 times 3 plus 4, 6 plus 4. The mid-segment is 10, and we can check. 10 is half of 20, so we used our new property correctly. So let's add that into our Freyer model. Mid-segment. Line inside of triangle made by connecting two midpoints. And our formula for it is mid-segment is equal to 1/2 of that third side. All right. So that is our triangles. Most importantly is that third fact or characteristic. We're going to quickly run through all the other quadrilaterals that we have as a nice little reminder. So we have triangles and then we have quadrilaterals, which the definition is a four-sided polygon. This includes, which we're going to talk about next, it includes kites, it includes trapezoids, it includes rectangles, it includes parallelograms, it includes rhombi, and it includes squares. It does not include pentagon, it does not include circle, it does not include triangle, it does not include this shape that's four-sided but not connected, right? We will learn some facts and characteristics, but we're just going to use our definitions for now. Our kite, all right, is a quadrilateral with two pairs of congruent consecutive sides. Consecutive just means next to each other. So again, our examples, we could have a kite like we were used to seeing in the sky. We could have a sideways kite that looks more like a fish, possibly. Right, but usually we will see these tick marks. That means we have two pairs of congruent sides, but they're next to each other. All right. Facts and characteristics, we're going to skip. We'll come back and talk about that in video number 2. Non-examples. A rectangle, right, has two pairs of congruent sides, but they're not consecutive. A parallelogram, again, two pairs of congruent sides, but they are not consecutive. And what you guys prefer as a diamond, which I will call a square or a rhombus. All of these sides are the same, so this is not a kite. I guess we could call it a kite, but we probably won't. The next one, we call it a trapezoid, right? Which is a quadrilateral. With exactly one pair of parallel sides. All right, so what that means is we have a trapezoid, or we have a trapezoid, right? Or we have a trapezoid, or we have a trapezoid. But in all of these cases, we see exactly one pair of sides that are parallel. The other pair of sides are not parallel, right? This differs. In some textbooks, we're going to say it has to have exactly one pair of parallel sides. Now, an example would mean a rectangle, because it has two pairs of parallel sides. A parallelogram, again, has two pairs of parallel sides. These are different from a trapezoid. We're going to also talk about a isosceles trapezoids, and that's when the legs are congruent, but we'll come back and talk about that a little bit more in detail later. We have four more that we're going to talk about real briefly. The next one is parallelogram. All right, definition, and I kind of alluded to it. It is a quadrilateral. I'm just going to shorthand it as quad. Quadrilateral with exactly two pairs of parallel sides. All right, so our stereotypical parallelogram kind of looks like this. But if we have those parallel sides at right angles, it could look like this. But notice how I'm adding those parallel symbols to everything. We don't have to have the sides look that different, right? They could look more like all the same, just like in a square, right? We have two pairs of parallel sides. Non-examples would include, right, that trapezoid where it only has one pair, right? Let's keep moving on. We have rectangles. All right, definition, a quadrilateral taking a pause here to make sure that I'm saying it word for word from our Springboard book. Okay. Not a quadrilateral, a parallelogram with four right angles. All right. So we're specifying that we for sure know that it's already a parallelogram and it has four right angles. So rectangle we usually draw like this. And we usually just draw those right angle symbols in there. We don't have to draw the parallel symbols anymore. But some rectangles have all sides that are the same, and that might look like another shape. Some non-examples, right? Just because it's a parallelogram doesn't mean it's going to be a rectangle. We must see those right angles. Our next one is a rhombus. The plural is rhombi. All right, definition of a rhombus is a parallelogram with 4 congruent sides. All right, so that could be, right, this is usually our stereotypical rhombus. We have 4 congruent sides. We usually don't do the parallel symbols anymore because we have some other theorems in play here. And we also have a square, right? Even though it has 4 right angles, it does still have 4 congruent sides. So it is a rhombus. Non-examples would be a rectangle, right? Because clearly those sides are not all the same. Same thing with a parallelogram, right? These are all not the same size, even though they're parallel. The last one, and we've been using it as our examples, squares, right? Our definition of a square is a parallelogram with 4 right angles and 4 congruent sides. The only way a square is going to look like is what you already know, right? As 4 congruent sides and 4 right angles. Some non-examples could be, right, a parallelogram, a rectangle. It has 4 right angles, but not enough congruent sides, right? One side is definitely longer than the other. A rhombus is not a square unless it has those 4 right angles. So we're going to come back over the next couple videos and fill in the properties. But for now, our Fourier model should look like this. Hopefully you read the instructions on Google Classroom that said make your own by drawing this or print out the blank that I gave you. But stay tuned for video 2. We'll talk about just kites and trapezoids.